Welcome back. We were discussing regarding heat exchanger network analysis. We are halfway through. We have taken an example from the reference I have given from the paper of Linoff and Hinmars, and the example discussed in the same paper we have picked up, and so far what we have achieved, if we go little bit back. So, this is the problem table. By tabular solution we have find out the hot utility requirement, cold utility requirement and the pinch point. So, this is what we have identified, and then what we have done, we have told that once we have the pinch point, the problem can be divided into hot end and cold end, and the sub network, how the energy is flowing from the highest temperature to the lowest temperature, it is shown. It has to be remembered that highest temperature is the temperature of the hot utility available, lowest temperature is the temperature of the cold utility available, and this is how the energy flow takes place. Now, with that we will have, this is our hot end problem. So, hot end problem, from the hot utility this much amount of heat has to go. At the pinch point there is no heat transfer. This is the cold end problem. From in the cold end problem, this much amount of heat has to be dumped to the cold utility. Now, with this we have given certain rule. These rules are simple rules, but they are very important and they are based on laws of thermodynamics. With this I can take some example. Let us say these two are the two streams, and these are also these are 1 2, these are 2 streams and these are 2 different streams. So, 4 streams are there. So, difference in C, first thing is or composite C difference. So, it will be 8 minus 6, that is 2. See, this 1 2 3 4 are the stream numbers, and here 4 2 5 3 etc. These are the heat capacity rate. So, difference in composite C, what it will be? The composite C, in this side it is 8 and this side it is 4. So, 8 minus 6, that is 2, summation of match, that is what we have got, summation of match C. Suppose this kind of match we have got, that match we have proposed, that means there is stream 1 and stream 3, we are thinking of one heat exchanger between them. So, this is the symbol by which we will show a match. This shows a particular heat exchanger. Similarly, we are thinking another heat exchanger between stream 2 and stream 4. So, this is another heat exchanger. So, in this case what is the difference? In this case difference is 5 minus 4, that is the individual match difference, and in this case the difference is 3 minus 2. So, in this case this is 5 minus 4 is equal to 1 and 3 minus 2 is equal to 1. So, this is 2. So, solution is possible because we are considering the hot end of the problem. And here you see another kind of a example we have given, that here there are 3 streams and here there are 2 streams. So, difference in composite C, composite heat capacity rate. So, 5 plus 3 plus 1, that is your 9, and 4 plus 2, that is 9 minus 6, that is 3. And summation of match. So, we are considering one match between 4 and 5, that means stream 1 and stream 3, and another match we are considering between stream 2 and stream 4. So, in this case difference is 5 minus 4, and in this case the difference is 3 minus 2. So, this will be 1 plus 1, that is 2. Here also solution is possible. So, this is how we have to check whether we are obeying the pinch rules or rules at the pinch point, because as I have told, our design should start from the pinch point. Why the design should start from the pinch point? Because the condition at the pinch point is this most stringent. At the pinch point, we are having minimum amount of temperature difference allowable between the two streams. So, if we violate this thing, then our design is not according to the specification. So, we have to be very careful like this. It is at other places we will find that the temperature difference between the two streams are more than 20 degrees Celsius or pinch point, but here it is the minimum. So, we have to be very careful. We have to start the solution from the pinch point, and either we have to move towards the hot end or highest temperature end, or we have to move towards the lowest temperature end. So, this is kind of a logic diagram for hot end design. I do not think much explanation is needed. Whatever explanation is needed, I have put it in some sort of a flow chart, that this has to be satisfied. This is almost self explanatory, and this has to be satisfied. First, we have to check the number of streams, hot stream and cold stream. So, number of hot streams should be less than the number of cold streams, and if we satisfy them, then we have to satisfy for each match. If that does not match, then we have to go for stream splitting. Suppose the number of hot stream is not less than number of cold stream, then what we have to do? We have to split one cold stream into two cold stream. So, now the number of cold stream will increase. So, this we will explain as we proceed with the example. So, this is the hot end. So, hot end, there are, for the present problem of hot end, there are three streams. So, one stream start from 150 degrees Celsius, it goes up to your 90 degrees Celsius. Another cold stream, the pinch point for the cold side is 70 degrees. So, from 70 degree to 125 degrees Celsius, and another one is from 70 degree to 100 degrees Celsius. These are not the supply temperature of the cold stream. So, what we can think of? We can think of a match between stream 1 and stream 3. So, this kind of a match we can think of, and 120 will be the amount of heat exchange in this heat exchanger. So, by that we will be able to get the pinch temperature of the for the hot stream, and then we have not to bother regarding the hot stream, because in this end the hot stream is to be cooled from 150 degrees Celsius to 90 degrees Celsius only. So, we can tick off the hot stream. So, this is called tick off method. For other two cold streams, the remaining two streams which are cold streams, for them we do not have any hot stream to exchange heat. So, we have to use heat utility here, or rather hot utility here. So, we can find out what amount of hot utility has to be used, and we can solve this problem. The other thing is that this is not the only solution. We can think of another solution where at the pinch end, just adjacent to the pinch point, we can think of one heat exchanger between 1 and 4, and the amount of heat exchange is 90 unit. Then we can think another heat exchanger between 1 and 3, the amount of heat exchange is 30. So, by this we have satisfied the top stream, that means the hot stream, we can tick off it. We have satisfied the requirement of the stream number 4, this is the cold stream, we can tick off this, but the stream number 3 needs further cooling, further heating. So, one hot utility has to be used, and we can calculate how much hot utility is needed. And you will find whatever hot utility we have used by 2 heaters here or 2 heat exchangers here, same amount of hot utility has to be used, because this is the minimum amount of hot utility. So, you see here we get 1 heat exchanger, second heat exchanger, third heat exchanger. Here also we get 1 heat exchanger, then second heat exchanger, third heat exchanger. So, 3 heat exchanger in both the cases we get same amount of hot utility to be used, but the advantage is that we are getting 2 solutions. So, 2 options are available to the designer or design engineer, and depending on plant requirement one can take any one of these options. Now, if we go for stream matching for cold stream, so what we find, NC is less than equal to NH. So, that is one good thing we have found. So, this is satisfied, but for cumulative CC and CH, this is 8 and this is 2, these are the 2 streams, and the other side we have got 3 and 2.5. So, 2 and 2.5 matches, 2 is less than 2.5, but 8 and 3 they does not match, they do not match. So, this is not possible. Then can we match with 8 and 2.5, 3 and 2? You see, this side is the hot side, this side is the cold side. So, this match is not acceptable. This match is acceptable, 8 is higher than 2.5. So, this match is acceptable, but this match is not acceptable. So, this match is not acceptable and this match is not acceptable. So, without stream splitting we cannot have any answer in this case. So, while doing the cold end design of the heat exchanger network, we could see that we do not have any alternative, but we have to go for splitting the streams. So, generally in the cold end the hot stream is split, and hot stream there are 2 hot stream and the properties are given 8 and 2. The 8 is having a quite large value. So, let us think of splitting it, and if we split it, let us say we are splitting it into 7.5 and 0.5. Then 7.5 that matches very well with 3, because 7.5 is higher compared to 3, which is the cold stream, but 0.5 it does not match with the another stream, another cold stream, which is at 2.5. Similarly, the hot stream which is there with a value CH value of 2, that also does not match with 2.5. So, this stream splitting is not very effective. So, let us again think another kind of another stream splitting, that 8 is divided into 3 and 5. So, 3 is equal to the cold stream CH3. So, this match is possible, and 5 is larger than cold stream 2.5, CH value of cold stream 2.5. So, this match is also possible. So, this is one possible solution, that we the stream 8 that can be divided into two streams, and both these streams should be selected in such a way, so that either they are higher or equal to the value of CH of the 2 cold streams. Another kind of splitting is possible. Here what we are doing, we will see that 7.5 and 0.5 initially we have split the hot stream with CH value 8, and then 7.5 matches with 3, but 0.5 does not match with 2.5. So, the cold stream also we can split. Now, we are splitting the cold stream at 0.5 and 2. So, this 0.5 matches with 0.5, and 2 which is remaining of the cold stream, that matches with another hot stream whose CH value is 2. So, this is also one match possible. Now, you see this gives lot of flexibility, but exactly how we have to split, not only we have to obey the pinch rules, but also we have to consider the takeoff geometry, and when we will take up this problem in the next slide, then we will see how exactly the CH values should be split to have the takeoff logic correctly. Okay. So, one thing we get from here that splitting is necessary. Then I have shown two different possibilities of feasible split. There could be other possibilities. With this, we will go to the next stage of the problem, where we will exercise the takeoff geometry and takeoff logic, and exactly what kind of split is needed, that we will find out. So, next level, for the cold end, we get the solution like this. From the, so there is a stream splitting needed, and we have already shown the stream which is having 8 heat capacity rate, the hot stream, that has to be split into 2. So, here we are showing the stream has been split into 2. Now, you see we are starting from the pinch point, and one heat exchanger we propose like this, and how we have split the heat capacity rate, one is 3.5 and another is 4.5, these are the heat capacity rate. So, one heat exchanger we can consider like this, the next heat exchanger we can consider like this, and first heat exchanger after the pinch point we do, that means this stream's condition is matched and we can tick off this one. Then we can think of the second stream, second heat exchanger. So, this stream, this heat exchanger if we consider, then this stream which has to reach 60 degree Celsius, it can be brought to 60 degree Celsius, we can tick off this. For the third, we can consider a match between stream 2, between this stream, that means this is another heat exchanger we can consider, and with this this stream, third stream, that can be satisfied. So, if we do that, only the topmost stream which has to be cooled, so that is left, and here we have to use one cold utility. How much cold utility we have to use, you can calculate, and you will see whatever solution we have got. So, with that cold utility we will be able to satisfy this situation. So, this gives the solution of the cold end of the problem. So, with this we will be able to design the cold end. Other possibilities are there, we can have an alternative design of the cold end. So, we have got some alternative design of the hot end. If you see that we have got two alternative designs of the hot end, and we have got one design of the cold end. Of course, we can get alternative design also, and then we have got several alternatives, and then we can stitch. One possible hot end design can be stitched with one possible cold end design. So, then it will give the total design of the heat exchanger network, and our heat exchanger network synthesis is done. What we have got? We have got the minimum amount of cold utility to be used. We have got the minimum amount of hot utility to be used. We have got the stream matching, that which stream has to be matched with which other stream. We have got also the number of heat exchangers to be used, number of stream heat exchanger to be used, number of heat exchanger between streams, and number of utility heat exchangers to be used. So, all we have got, and that brings us to the complete solution of the heat exchanger network. I think it would be good for you, the reference is given. So, you can go to the reference, see the problem once again. Obviously, the reference gives much more discussion and some more insight. So, I would strongly suggest that one should go to the reference. The problem one can understand from the from whatever has been presented here, but more background material can be obtained from the reference. So, I strongly suggest to go to the reference. With this, I come to an end of this particular lecture, and now onward my colleague Professor Anandarup Bhattacharya will take up, and other topics of waste heat recovery and energy conservation will be dealt by Professor Anandarup Bhattacharya. So, thank you. Thanks to all of you.